Okay, let's start today's session. Okay, let me also share my screen. Right. So,
Yeah, we can wait for some more time, ma'am. Maybe more will join.
oh, right, right. Okay, okay, sure. Okay, now let's start. Whoever wants to join later, I'll admit that person. So, okay. Yeah, right. So now we are in the eighth week of this course DL4CV, and we have learned a lot about CNNs, neural networks, and so many things. So today, as we are going through the eighth week, we are going to walk through RNNs and LSTMs a little bit, and we'll see how these what these architectures are. So, sir has already in the lecture videos you have already gone through these things. I'm assuming, but yeah, this is going to be like kind of a revision of those things because RNNs and LSTMs are quite a bit different from what you have seen in CNNs and other architectures. So, yeah, it's better that we go through them. Right. So, those of you who are present, I mean, um, like, can you tell me, like, what is the difference? Tell me a very fundamental difference between, suppose, one image and a sentence, suppose, a piece of text. So, what is the basic difference between these two? Can anyone tell me?
Yeah, text is sequential in nature.
Correct. So text has this temporal thing in it, which the images don't have. So images are we have seen that comfortably a CNN works on images and it takes into consideration the local relationships and so on. Whereas text is a little bit different. First of all, it is made up of these not distinct, discrete entities called words. So words or tokens or whatever you name them. So it is made up of that, and it is kind of temporal. It's sequential. So it comes one after the other. So suppose when you let's think of it in this way that you have a suppose what you have a sentence and the sentence contains 10 words. So now the problem is that if you um, suppose again we go back to our grassroots level, we only know neural networks. We do not know anything fancy. So suppose you have this 10 words and you are trying to classify something, you are trying to identify something. Like one very intuitive example is sentiment analysis. So suppose I give you a sentence like this that the movie was excellent, I liked it very much. So this is your piece of text and you are trying to classify whether that's a positive sentiment or a negative sentiment. Now, what the problem is that obviously neural networks, they'll try to neural networks or anything with computers, they cannot I mean, they cannot process. Um, yeah, yeah, they cannot process anything which is not in numbers. Okay, so they cannot process the word, the movie is excellent and so on. So they'll need a number, some sort of numerical representation for it. And the way it goes is, uh, for each word in the text, they'll basically convert it to an embedding. Okay, so the will have an embedding vector, uh, movie will have an embedding vector,
Hello.
and so. Yeah, hello.
The first slide is visible.
Yeah, yeah, I have not gone into it.
Okay, okay.
Yeah, I'll just go into it, just giving you a brief background of why we need RNNs. Right. So what happens is that suppose, suppose you have a 100 dimension vector that represents each word, right? And your sentence consists of 10 words. So now you, in order to process this entire sentence by a single neural network, what you will need to do? So you have 10 words, 100 dimension vector per word. Right. So then what you have to do is, in order to process everything together, you'll have to kind of like, flatten the entire thing. So you'll have a like a stack of, uh, you know, word vectors, each of dimension 100. So the stack size will be like 10. So because you have 10 words. So it will be like you arrange first the vector for the, then below that it will be the vector of movie, below that the vector of is, and so on. You arrange this entire thing into and concatenate to make it a single vector, which will be of dimension 10 cross 10 into 1000, because you have 10 words of 10 into 100, sorry, because you have 10 words of 100 dimension each, right? Now this 1000 dimension, so this doesn't look very bad, because we have so much compute, and our computers are so advanced these days. But because of these because of these 1000, now in order to in order to process this 1000 dimensional data, you will have to create a appropriately large W matrix, which basically is required to forward propagate it to the next layer in the next hidden layer in the neural network. So because of this, what happens is you have a lot of weight. Okay, so every for every I mean the bigger the sentence becomes. So obviously another thing is that this sentence is of 10 words, another sentence may be of 20 words. So then your neural network basically fails, because you had created a W matrix which was suitable only for 10 words. Now you have a other sentence which consists of 20 words. So as and when your sequence length increases, you see that your neural network, first of all, it's very difficult to accommodate every sentence into, a fixed architecture like this. And second of all, as and when your sequence length increases, number of words in your text increases, your matrix also becomes bigger and bigger, until there'll come a point when your computer won't be able to the W matrix will be so big that your computer will not be able to process it. So that is why people came up with this architecture called RNNs, so recurrent neural networks. So this is another neural network, another specialized architecture, which where um, so first of all, there are two main functionalities of this, that it is able to deal with sequential data. So not only we generally think of RNNs and text as synonymous, but that's not true. So RNNs can be used to deal with any sequential data. It can be used to deal with temporal, any time series forecasting data, any temporal data that has a sequence to it. So this is why RNNs are, nowadays, so not nowadays, but RNNs came into being. The use case being that I want to process something sequential, so I should have the freedom to choose a your to choose a sequence length of my own choice. First of all, it should not be that all my sentences should be of size 10 in order to accommodate my neural network. It can be anything, first of all. And second of all, I want to stop this explosion of weights, right? I want to lessen the number of parameters required to process some big thing like this. So that is why this notion of RNNs came up, right? So what you have is, in the input you have, suppose, a sentence or a piece of text like this. So suppose your we have already broken the text into these tokens x1, x2, up to some x small t, x small t plus 1, and so on. And now what we'll do is we'll train it in such a way that for each word we'll use some weight matrix, and the same weight matrix will be used by the second word also, by the tth word also, by the t plus 1th word also, right? And if you are able to, so imagine in the previous situation what I said, that you need to club all your words in the text together, and based on the resulting dimension you need to create your weight matrix. Here what you need to do, here suppose all of these are, suppose, 100 dimensional, as we had thought of in the beginning of the session, that each of these word vectors are 100 dimensional. So now you do not need to concat them, you do not need to flatten them or anything. All you need is, you need a weight matrix that will compute. So this first, let's think of this as a black box. Any neural network that is there, we'll talk about what is going on inside this later. But suppose you have a neural network here. So all you need is a W matrix which can process this input dimension of 100 instead of 1000 that we saw in the, in the 1 or 2 minutes back. So that is the advantage of RNNs. They can process sequential data by, because of their architecture, and also they save a lot of parameters. There is a third advantage to saving. So saving parameters is not the only goal that we have. Okay, so first of all, I mean, nowadays we have a lot of resources, and as and when the time is passing, we are getting more and more bigger and bigger GPUs and all. So let's forget about compute for 1 minute. But it has also been seen that, so in general, suppose you have a text like this. So as I said, let the sentence be, this movie is amazing, I liked it very much. So if the sentence is like this, so the weight vectors should not be like, they should not be segregated for the individual words. Okay, so for example, the word the, it should not have a different weight vector. The word movie, that should not have a different weight vector. So if you are basically keeping different weights, different learnable parameters for each of these words, each of these pieces of tokens or words, then basically it's very difficult for your neural network to learn and aggregate information from all of these. So what this kind, so this parameter sharing that I'm talking about, where you share your weight matrices between words, across words, the advantage is that the same weight matrix is learning for this word, this word, this word, and this word. So the aggregate information that you want to extract out of this sentence, that is being learned by a single weight vector. So that is another that is kind of the third advantage of using an architecture like this. So just going into a little bit detail of how it happens. So it's very simple. What these RNNs comprise of is a very important hidden state. So this hidden state kind of is responsible. This is the neural network. This hidden state is the neural network where you kind of you contain two information. One is the current word that is there, and the other is the previous hidden state. Okay, so that is what RNNs are made of. Why previous hidden states? Because it's more understandable in this step. Suppose when you are processing this t plus 1th word, you want the first of all, you want the neural network to learn the information of this t plus 1th word, plus you want the neural network to remember what was going on previously, because none of the words are disconnected, all the words are related. That is why you need previous information. So that is why this previous hidden state thing comes into be. So the formulation of the hidden state is like this. So all of this already has been taught in this week's class, but just a little bit of recap, that at any point your current hidden state is made up of something like this, where So you first take your previous hidden state, which gives you information about all the previous words that were there, right? Then you project it. You use a some weight WAA on top of it. So then what you do is then you take your current word, which is xt suppose, and you take another weight matrix WAX and multiply xt with that. The purpose being that AT minus 1 and xt are basically vectors in two different vector spaces. You need to project them to the same vector space. And that projection is learned by these two weight matrices. So you basically add them up and add a bias term, and then on top of that you place some activation function, and that becomes your current hidden state. So this is your neural network, which is your current hidden state, right? And so now that you have computed this A of t, now what you need to do is, suppose you want an output from this particular hidden state, then all you have to do is, there is another uh, weight matrix WYA. So what you have this hidden state A of t. So you just multiply this A of t with this particular weight matrix, and this is just a normal linear layer. So WYA into A of t plus B of y being the bias, and you pass it through some activation function G2, and that becomes your YT. So basically from this space you are projecting to the Y space, and that gives you the output for the Tth location in the sequence. So that is what is the functionality of an RNN. And here note that the learnable parameters are this WAA, WAX, BA, WYA, and BY. That's it. So this is all of these WAA, AX, WYA, all of these are shared for each word. So it doesn't change when you change the word number. Unlike, so if you go back and try to compute what happens when you use a normal ordinary neural network to process text, you will see that these things are not remaining the same, or they are much, I mean, for each word these things are changing, whereas in here it's intentionally made to be the same. These things will be shared between words. That is what why we call it parameter sharing, which is also one feature of CNNs and also another feature of RNNs, that parameter is shared among words in this kind of an architecture, right? So while this looks fine, everything looks good. We are now processing text and all in this way temporally, where we are also kind of we are using the current word, and also we are kind of using the previous information in the form of a hidden state in order to generate some output. But there is a problem with this sort of architecture. This problem is called the problem of short-term memory, which happens because of something called the vanishing gradient problem. Okay, so just to let you know, all of our slides for this week are mainly from some Medium articles and some, Stanford lectures. So just a courtesy mention. So what they have said here is that recurrent neural networks suffer from short-term memory. So if a sequence is long enough, they'll have a hard time carrying that information. So what happens is that, suppose you have suppose a 20 length sequence, 20 length word, 20 length sentence suppose. So it starts from here. So it this cell, this hidden state basically processes some information about the first word, then this one about the second word, dot dot dot. By the time it has gone to the 19th and 20th word, what has happened is that it has forgotten mostly about the 0th and first word, or first and second word if you start the text with one. So this is what has happened. So by the time it has reached here, it has forgotten all about what was going on here, and that is not good. So if you have a sentence where um, you know you need to, in order to understand it, suppose your 19th word is dependent on the first word. In that case, this will cause problems, because by the time you have reached position number 19, you have already forgotten what is going on here. So that is what is meant by what they're saying here, that they'll have a hard time carrying information from earlier time steps to later ones. So if you're trying to process a paragraph of text to do predictions, RNNs may leave out important information from the beginning. So that is why RNNs are good as long as your text is small, right? So as and when your textual length it starts increasing, RNNs start causing problems, right? And what is this vanishing gradient problem? It's because when you are back propagating through it, chain rule, because of the chain rule, it becomes such that, so when you are back propagating, what happens is you take each weight that is there and you do an update on top of that. So during your gradient descent algorithm, so what happens is your new weight becomes old weight minus learning rate into the gradient. And now, because what this vanishing gradient problem is that, suppose, okay, yeah. So what your vanishing gradient problem says is that, suppose you are at the 20th time step. So now when you are back propagating through it, and what happens is that when you have gone back, suppose at time step 2 or something like that, then your gradient, you have gone on multiplying so many gradients together. So because of, so and weight vectors, weight matrices, these values are anywhere very between 0 and 1, suppose. So if you multiply so many values of so many times, I mean values between 0 and 1, if you multiply them so many times through the chain, then what happens is that your values become extremely small. That is why the gradient of these kind of architectures become extremely small. So it's like this. So 2.1 was your original weight. You multiply something extremely small. Uh, you subtract something extremely small from it. The resultant value is not much different from it, right? So vanishing gradient problem, what it causes is that, because your gradient is almost becoming very 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 small, it's almost vanishing. That is why what is happening is that there is hardly any learning. So this weight, whatever it was, it is still very close even after the update. So the solutions that have been proposed to solve this problem constitute two very very popular architectures, LSTMs and GRUs. Okay, so how are they different fundamentally from with respect to um, you know RNNs? So first of the biggest contribution that these two architectures have is that LSTMs, so they theoretically stop this vanishing gradient problem, so they do not forget what is going on, even in the, so in the 20th time step, what happened in the first time step, they try to remember all that, and theoretically they never forget what they saw before. So that is the advantage of these two architectures. So that is why people have come up with these, and in the modern times people don't use RNNs, they use just these two. So, what is going on inside an LSTM? We'll probably look at the LSTM in a little bit more detail than GRU, because GRUs are very very similar to LSTMs, just maybe a little bit toned down. So, LSTMs, what they have is, in the RNNs we saw that there's a hidden state that consists of the hidden. It consists of basically the previous information, right? What happens in an LSTM is they have a hidden state and they have something called a cell state. Okay, so this cell state, so it's generally kind of thought of as like kind of memory. Okay, so the cell state is responsible for it. This is the one that is responsible for not causing that forgetting thing. So here what we saw that it's not carrying the information from earlier time steps to the later ones. So that is stopped by this cell state. So it is like how our brain processes. So it keeps certain inform. So when whatever it saw in the first time step, it will try to keep certain information, some of the necessary information out of that first time step in the 20th time step, such that you can now your model knows how the first and the 20th words are related. So that is what is meant by the cell state. And there are four gates basically. forget gate, input gate, output gate, and there is another gate. I'll go through them. So 3 or 4 gates, the different variations of LSTMs use different number of gates. So here we'll see that actually 4 gates are used in the LSTM, and yeah, so each of these gates have different purposes. So we'll go through what each of them are. So what is written here is that these gates can learn which data in a sequence is important to keep or throw away. By doing that, it can pass relevant information down the long chain of sequences to make predictions. So that's what I said in a nutshell. That using this cell state and these different gates, which have different functionalities, the network itself can learn what information to preserve and what to throw away. And once it learns that, if suppose then it learns that at time step 1, the word that is there at time step 1, the word w, suppose here this x1, this is somehow important to process this x20, and that is why it keeps some information from this x1 and passes it to x20. But suppose there is some x5 which is not required for x20, so that information is thrown away at this stage. So that is how the problem of forgetting is solved, right? So here, actually, if you go back and look at this diagram once again, you will see. So initially, people who are learning LSTM's GRUs, it might be confusing, but yeah, once you look at the diagrams, it's pretty simple to understand what's going on. So just a little bit again, talking about the core concept that is going on in LSTMs is that, again, what I said about the cell state, it's like the memory of the network. Okay, it can carry relevant information throughout the processing of the sequence. So even information from earlier time steps can make its way to later time steps, reducing the effects of short term memory. As the cell state goes on its journey, information gets added or removed from the to the cell state via gates, right? So the cell state is kind of the memory, and how you control that memory is dependent on the learnable gates. So the gates are made up of weights which the model learns. Okay, so there the model decides itself by itself that given a cell state, so cell states also traverse through time. So at cell 20, at cell state 20, at t equal to 20, you are basically trying to decide what uh, through the gates, what information do you require and what information do you not require, and based on that, some information is retained, other information is thrown away. So this, because LSTMs became very popular because of this different kind of sort of way of thinking, like keeping this memory and then allowing gates to kind of choose which memories you want to keep, which memories you do not want to keep. And basically cell states are nothing but, it's like whatever your gates decide to do, you store that information in the cells. It's like cells of the brain, you store all these information in your cells. So that is what the cell state looks like, right? So there are generally if you look at the literature of LSTM, there are 3 or 4 gates. So here I'm showing what happens, I mean the variation where people use 4 gates. So this slide is basically from one of the website, I mean from the CS, for what is it, I forgot. Anyway, it's from the Stanford NLP course. So let's go through it. Types of gates. In order to remedy the vanishing gradient problem, specific gates are used in some types of RNNs, and all of them have a well-defined purpose. So it's again one issue that people face with LSTMs is okay. Somebody unmuted yourself. I mean, can you, yeah.
Abhilash, Abhi, ma'am.
Yeah, yeah.
Hello. Ma'am, actually, I have some issues in some problem. Manogina ma'am has explained that, but I am not getting the calculation. Can you explain that? These theories we did it.
Okay.
I have one previous year question.
Tell me.
I'll tell you the question. That means I have to find out there is a gate, LSTM gate, okay?
Correct.
LSTM gate, and there are hidden states of 3 dimensions and 4 dimensions, okay? and
Okay.
there are x1, x2, x3, x4, and they have the dimensions. And u1, u2, v1, v2, all these things are given in some figure. I will show you the figure also. Okay, sir, ma'am.
Okay.
And you have to find out the probability of that. Can I show you? Can I show you? It's very important, that question.
Okay. Can we talk about it sometime later, maybe?
Okay, okay.
We'll.
You complete this one, then we
Yeah,
can
yeah,
start
yeah,
with that.
yeah, yeah. That will be
Okay,
better.
okay.
Okay. So right. So there are basically these. Can you please mute yourself?
Okay, sure, ma'am.
Yeah, yeah. Thank you. Right. So this particular table, yeah, this particular table is actually meant for both LSTMs and GRUs. And one thing is that people generally keep on confusing like how to remember LSTMs and all, but I generally remember them using the gates. So once you understand the gates, I think it will not be very difficult for you to remember. So there are these four gates, and so just remember the signs for now. This what is this? This something, this what sign is it? I've forgotten whether delta or lambda or something like that. So this delta u.
It's gamma.
Oh, sorry, thank you so much. So yeah, sorry. Yeah, so this gamma u, gamma r, gamma f, and gamma o, these are the four gates. Just remember these signs, and let's go through it. So in the final architecture, so you, what do you have? You have a in an LSTM you have a current cell state, you have a normal cell, you have a normal cell state, you have a hidden state, sorry. So the current cell state is what you, inside the current cell state you combine, you basically compute a combination of what you had before and what you want to what new you want to learn. Okay, so it's like this that okay, yeah, one clarification is that inside this, sorry, inside this current cell state you will basically consist take the first of all you will have this current input xt, and then you'll have this older input and this gamma r. Okay, so this means what, that kind of what it, the story will go on like this, that you are here trying to decide that in your current cell how much information do you want to retain from the previous hidden state, and how much information do you want from the current word. So that is what is calculated here. Okay, instead of, we'll go through the LSTM first because that seems more intuitive to me. So that is how you create the current cell state. That is the first thing. Second thing is that now you have created the current cell state, but you have to make some revisions from it in order to get your actual cell state. So how do you do that? One is that you have a current cell state which you have somehow created from your current input and previous outputs, previous learning. Now what you need to do is you take some parts of it, some parts from that current cell state, and some parts from that what do we call it? Yeah, some parts from the previous cell states. Okay, so that is why this gamma f is called forget gate. What happens here is that you choose that, okay, whatever was there in my previous cell state at time step t minus 1, how much do I forget about that? So that is given by this forget gate. And this other gate, this kind of says that, okay, I have computed this current cell state here in this particular step. How much do I keep? How much knowledge do I keep about that cell? Okay, that cell state basically. And we combine them to get the final cell state of the current time step. And there's also all of these, you'll see they are dependent on the previous hidden state as well. So the hidden state is computed as following, that it's what you do is, so now you have, in this step you have computed the final cell state of your current timestamp, and you are basically again through a gate you are deciding how much do you want to retain out of that in your current hidden state, right? So that is the understanding of LSTM. So if you want to remember LSTMs, the best way is to understand what the functionalities of the gates are. So once you get that, LSTMs, GRUs, these will be very easy to understand, because all you need to remember is what the steps are. You first create your current cell state. From that, based on your current input and the previous learning, whatever is there, From there, you do not use this current cell state as your final cell state. So there's a final cell state as well, which is dependent on your current one and what you learned from the past. Okay, so now your cells are created, this cell state is created here, and now because you have a hidden state also that uh, you know uh, on which your cell states are dependent, you need to update this as well. So this is also dependent on your final cell state CT. So this is the sequence of this is the story that is going on in LSTMs, and a similar story goes on in GRUs. So basically GRUs, they consist of, as we see here in this table, they consist of only two gates, update gate and relevance gate. So how much past should matter now is the update gate, and do I drop previous information, that is the relevance gate. So yeah, so just in a nutshell, the dependencies are very similar in the this current cell state is created in the same way, where it is asking in the current cell state how much of the previous information is should matter. So you use that using the current cell state, and use that using this what gate is it, the relevance gate, and then you have this where basically you what they have done here is in the update gate, basically you'll see that many of these gates in the LSTMs are really very related, and there's a very thin line between them. So maybe one is the complement of the other. So the GRUs, what they have simply done is they completely get rid of this hidden state. I mean, uh, yeah, what they do is basically they they basically get rid of this forget gate and other things. So they just keep two gates very neatly, and they are the hidden state equal to this current this final cell state. So basically it's almost like saying that you only have these cell states and do not have the hidden state. So in that way, the idea is very similar, that here also, out of the current cell state, how much do you keep, and from the previous cell states, how much do you forget. That is all that is there. That is all that you need to remember. So basically, if you look at functionalities, if you ever go to implement some NLP task like sentiment classification and all, you will generally not find any difference between these two. So people still prefer LSTMs, but yeah, GRUs you can use if you want your computations to be faster, because there are two gates less. So if you see, each gate would mean that there's a W matrix associated, U, and some bias associated with it. So the more the gates you have, the more the parameters you have. So in that way, GRUs are faster because the number of parameters that you want to learn are less. So just a little bit more detail, like what are bidirectional RNNs? Bidirectional RNNs are nothing but again, when you have, so here the hidden states. So previously I was saying as if you can only learn from the past, but in all tasks you do not need to assume that you do not have access to the future, right? So suppose you want to do sentiment classification on this same sentence, the movie is amazing, I really liked it. So in order to understand sentiment from it, you do not only need to look at the left, you can also look at the right. So uh, suppose you take this x2 word, so it's for processing this x2, you can look at x1 also, x3 also, x7 also, right? So that is what is meant by bidirectional RNNs, that uh, you can basically use these for you can go both directions, both towards the left and right. So the same thing, just that you have now two directions available. So these kinds of things are useful in sentiment classification sort of task, where you have a text piece of text, and you do not need to uh, you know what you need to do is, based on that piece of text, you are suppose classifying something. So then you can use bidirectional RNNs as and when you require, but they cannot be used for tasks like language modeling, because language modeling means what, that you are basically learning how to generate a sentence. So when you are generating a sentence where you are generating one word after another, you cannot see the future there because you are generating one word after another. So you are generating x2 from x1, xt from xt minus 1, and so on. And that is why when you are generating xt from your past information x1 to xt minus 1, you do not have access to this xt plus 1. So that is why in language modeling based tasks these are not really used. And what about deep RNNs? Deep RNNs are nothing but the same thing again. Okay, this image is enough. The same thing again, just that now you have, instead of one layer of hidden layers, you have, just like neural networks, you will have multiple layers of hidden states. So that is what is deep RNN. So more or less the RNN, whatever theory we had is done. So let's quickly look at some fun coding experiments. So did I? Okay. Delete these two first. Yeah.
Please zoom it.
Yeah,
You
I'll do
cannot
that.
see.
Yeah,
Yeah.
yeah, okay, sure. Is this better?
It's fine.
Okay, thanks. So let's start running. And so this example, why I chose this one is because we talked about text throughout the day, and I thought that looking at it from the textual point of view will actually make things it easier for to understand and interesting as well. So suppose Suppose we have a text like this. So, hey, how are you? Good, I am fine. Have a nice day. So, one is that, so here they are basically, in this cell, they are basically showing some examples as to, how to look at these pieces of text. So, one is basically, so what you need to do is, in order to do some language modeling or some, suppose say character prediction, word prediction, etc. What you need to do is, whatever text you have in your vocabulary, in your training set or vocabulary, you need to basically not vocabulary but corpus. So what you need to do is, you basically need to take all of these into account to understand what are your unique words, that are there in the training set. So that is what they have done. So first they have, if your corpus suppose has, corpus means just a list of sentences that you have, or text pieces that you have. And so what they have done is, in this step they have just joined it, and then so in this particular step what they have done is, for each character they have assigned a number. Okay. So yeah, so this is actually the opposite one. So here, as it says, you create a dictionary where each integer is mapped to one character, and similarly there's an opposite dictionary where each character is mapped to one integer. So again, if you run this one, what is seen here is that there is, so you have these, all of these letters are there, and what you do is, you simply assign a number to them. So O has been assigned the number 0, R has been assigned the number 1, and so on. Right. So the max, then also what you need is, you need to find out what is the max length of, what is the max sequence length that you have out of all your all sentences or all text that you have. So here we see that if we go character wise, the maximum length out of these three is 15. So that is what is calculated here. Right. So now what you have to do is, in order to make the procedure easier, since you have at max 15 characters in a sentence, what you have to do is, in the other sentences where there are less than 15 characters, you need to pad them up and you need to make them equal to 15. That is what is done here. So a padding is done. So using the space basically. So if a sentence has suppose 10 characters, you add 5 spaces at the end of it to make it 15. Right. So now, mm, right. So what they are doing here is, you need to now train this model for character prediction. And now because you want to do character prediction, how should your training data look like? One is that so suppose, yeah, how does character prediction happen? Very quickly, let's go through this. We'll also go, yeah. So suppose you gave the word A, you gave the character H, then the model should predict E. Then you then you gave the character E, the model should predict Y, and that is how it goes on. So in order to create the training data, that is why what you have to have is each of the letters should be given in the training sequence, and in the target sequence you should give the next letter. So that is given by this particular these two lines. So you take the start from the 0th character and go up till the second last character. This becomes your training set, sorry. And what your target becomes is you start from the first character until the last character. That becomes your target. So yeah, this is how your input sequence looks like. So hey, how are you? So the u is not there here. So the target sequence is for H, the next character is E, for E the next character is Y, and so on. And for this O, the next character is U. So this is how the input and target sequences look like. So now, as I said, that all the characters, computer cannot process these words, so you'll need to define some numbers for them. So that is done using this input sec and output target sec. So basically what you do is you find for each character that is there here, you find out what was the number associated with from this dictionary cat to it, and you basically append that. Okay. Now in this step what they do is there's a one hot encoder. Okay, let's run it first. Yeah. So now as I said that you need to, instead of sending a particular letter or a particular word, you need to send a vector for each again for each unit of text as you define it, whether it's a word or a character. You need to send a vector with numbers. So that is what is done in this one hot encode uh, uh, function basically. So I'm assuming that you people know what one hot encode is. Just that, suppose you have the character E, and suppose you have all the 26 characters from A to Z. So there'll be, suppose you have, then what will happen is you'll have a vector of 26 dimension where all will be zeros except the fifth position because your character is E. So that is what is meant by one hot encode. So basically in this way, if you take suppose hey, the word hey, H-E-Y. So H will have one such representation where only the position of H will be 1, others will be 0. E will have another such vector, Y will have another such vector. So in this way, every letter, every alphabet, or every character in your text has a separate vector. Right. So here basically, so did I run? Yeah. Yeah. So here basically this is how they one hot encode everything. So there were 3 sentences. Okay. And sequence length is taken to be 14 here because initially it was 15, but in the training set we made it 14. I mean 15 minus 1. Right. And one hot encoding size is 70. So this is based on how many letters you have basically. So based on your vocabulary, this size basically depends on your vocabulary that you create from the training and test set. So now you combine these two torch tensors, the input sequence and target sequence, and these are some very small details about about the CUDA and all. And this is finally your model. So in the model there is this RNN. So there's this so it comes with a, so you have to this is how you basically create RNN models in PyTorch. So you have this nn.rnn class where you initialize it with an input size, hidden dimension, and number of layers. So number of layers is basically this depth that I talked about. So yeah, and on top of this you have a fully connected layer. So it's like you are trying to predict at So you are trying whatever you are trying to predict, you have to do that using a fully connected layer. So that is what is uh, defined by this, and the fully connected layer has a dimension of hidden dim cross output size. So you are basically projecting from the hidden dimension as shown here in the first slide. So yeah, you have the hidden dimension and you have a matrix on top of that. So that just that. So that is why you have an nn dot linear where your first dimension is the hidden dimension. So that's it. So there's this the forward function is something like this, that your hidden state at first, generally either in the first step, in the 0th step basically when you have not started processing, is ideally I mean either it's all zeros or it's initialized by random values. So here they have initialized it using zeros. So now you this function basically initializes the first hidden state. So you get the first hidden state and then you do this. So you give your input x and you give the hidden state and you get the output and the next hidden state. So now yeah, so now what you do is, in order to look at everything, so in order to, so in the output also you are getting the sequence, some sort of a sequence. You are basically flattening that sequence in order to be able to process it through the fully connected layer. So that is, so you pass it through this self dot fc and you get the output. So I think these are fairly easy to understand. Did we run this? Okay, now again quickly. So we initialize the model with some input size, output size. So input size, you see the dict size, which is basically your vocabulary size, and output size also is the vocabulary size. Hidden dimension 12 and n layer equal to 1, which means that it's a single layer RNN, and you run it for 100 epochs with an LR of 0.01. The usual cross entropy loss is used, and with an atom optimizer. So this is your yeah. So this is your training sequence. Okay, it happens pretty fast, right? So because it's such a small data set, it happens very fast. So yeah, here what is happening is that every step you are basically predicting what is your next character, and the loss that you are incurring because of predicting a wrong character is this cross entropy loss, right? So in the training also we have seen training scripts like this for quite long now. So yeah, so this is how the training happens. You can see that the loss was pretty high before and it keeps reducing, and obviously yeah, so this is the predict function where you give a sequence, a little, I mean an incomplete sequence to the network, and by virtue of learning the weights, now the network will predict some, some other characters for you. So it looks like it. So what happens, I mean these are two functions for that. So for prediction and for sampling. So sampling is what that okay. Okay, just a second. Right. So sampling and sample and predictions are functions just for that. So sample means what, that suppose what they're doing here is they have started with some starting string like hey, and its target is that it has to predict characters for this many numbers, this many length, right? So this predict function and sample function are doing that. So they are generating iteratively, they are generating character by character until this outline length is exhausted. So yeah, so when you give a line like good, it's like it's returning good, I'm fine, which is kind of like I think the sentence that we saw upwards. Yeah, it looks like that. So this is actually here the model has learned so well that it's returning something that it already saw. So when you have a lot of training data, thousands and millions of sentences perhaps, then giving the word good will return you something pretty amazing. So yeah, I mean this is simply put what an RNN is. And yeah, now somebody was asking a question.
Hello, ma'am.
Yeah,
Ma'am, let me share the screen. Then I can show you the question.
yeah. Sure, even I'm not very confident with RNNs, but yeah, we can give it a try together.
Please,
Yeah.
please.
Okay, let me stop presenting.
Ma'am, please allow me.
Oh, where do I
Uh,
allow you?
you have to allow me.
Okay. Actually, no option is coming up for me like that.
Because
Let
here
me.
I'm.
Okay. No, I'm not getting any request actually for.
Ma'am, I'm actually previous years it was a question. Okay, so but I have to. How can
Okay.
I show you? I have to show you the question. Otherwise, it's not possible
Yeah.
to.
That's what I mean. I'm not getting any request. What you can do is you can mail it to me, and then we can have a look at it.
Ma'am, do you have the previous year's assignment questions?
Not at this point. Previous years or previous assignment. What are you
No,
saying?
previous years.
Okay. At this point, no, I do not have. If you have any link, you can send it to me.
Okay, I'm
Send as
sending
a
you that
chat.
just now.
Yeah.
Just now I'm
Or
sending.
what you can do is you can click a photo of your whatever you have, and you can send it in the chat.
Chat. Okay, I'm taking a photo. Please
Yeah.
wait,
Yeah.
ma'am.
Okay.
Ma'am, there is no option to send photo.
There's no option to chat, is it? I
No,
mean,
there is no option to change. Chat isn't available at this time.
oh, okay. Then, okay, send me the link of the assignment then.
How, ma'am? There is no option available to chat.
Oh, it's generally available for everybody.
No, nobody can. Like, yeah, ask anybody to chat. Say hi.
Okay, can others try also?
No option is not available.
Oh man. Okay. Then, okay. See the what we can do is you can send it to me, and I'll have a look at it, and then
Ma'am, ma'am, ma'am.
reply.
Yeah, you please tell me your email ID. I am sending you just now.
Okay, sure.
Uh,
Just I've pasted it.
okay, Abhip Shabasu.
Mhm.
ABHIPS Abhip Shabasu. I'm sending you just now.
Okay.
At the rate IISC dot AC dot in. Okay, I'm sending you.
Mhm.
Please wait for 2 minutes, ma'am.
Yeah, sure.
Ma'am, I've sent. Please check.
Okay. What is it on? Is it on RNNs only?
RNN. It's RNN.
Okay. BPTT or what?
Yeah. Normal RNN. Okay, it's a
Mm-hmm.
RNN having 3 dimension, 4 dimension hidden layers. Okay,
Okay.
it's there. You got it. Please check,
Just
man.
yeah. I'm just refreshing the mail page. I mean, it has still not come. I'll just
Uh,
check once again. Yeah, it came in my mobile, but not showing up on my laptop somehow. Let
okay.
me open it. Yeah. I just got it on laptop. Okay. Okay, there are two attachments. One
Yes,
dot
ma'am.
png has come two times. Both are
No,
same, is it?
no. They both are not same.
Okay.
Please check.
Just a second. Let me share my screen. Yeah, it's visible, right?
Yes, ma'am. Screen is visible, but the question is, this
Yeah.
question.
Mm-hmm.
Uh, This is the figure, and the
Hmm.
second part is there. One more figure is there.
This one.
Huh?
I think.
Figure now. What the question starts from the next. Yeah. I've sent you three.
Oh, is it? Here
Uh,
it's saying two attachments.
One more I have sent.
This one, is it?
Which one, ma'am? This is one. You got same attachment, I think, huh?
Yeah. That's what I was saying. That
Okay.
probably. Yeah.
One sec. I'm sending you once more. The main question is that two KPH. I've sent one. Please
Okay.
check.
Okay. Let me refresh. Okay. Okay. So they have given the vectors x1, x2, and x3. Yeah. Okay. So Swaroop, what was your question exactly? I'm still audible, right?
Ma'am has said, the Manogna ma'am, that you multiply u1 x1 at the first layer. Okay,
Yeah.
u1 x1. Okay, fine,
Correct.
I understood. But u1 x1 I cannot multiply
Okay. Why not? Because
because
because the dimension is not matching, right?
dimension is not
Yeah,
matching.
so that's what I mean. Some all the times, I mean, what you have to do in case of neural networks is you'll have to probably what do you call it? Transpose it at times in order to match their shapes. So
But I have to transpose it.
yeah.
Okay. Transpose and then solve it.
Wait, let me check once. Yeah. So since you can see that U1 and X1 are not matching, right?
Uh-huh.
So they'll match right when you do a transpose. So
Okay.
very often, suppose when you are doing backprop also, you'll often see that your dimensions are not matching. But when you
Okay.
do a transpose, it's matching. So in those cases, you have to do a transpose.
Ma'am, please go to the figure. First figure. The diagram. Yeah, the diagram.
Yeah,
Ma'am, what is happening? U1 X1 I am doing, and I am going to H naught. This one, this part, H naught.
correct. Huh?
Okay.
Huh?
Similarly, U1 X2 I am going.
U1 X2, yeah,
Similarly, I am going U1 X3.
correct.
Then from here to, if I have to go to the second part, na, the
Correct.
u1 x1 plus h naught v1,
Wait.
it will go to the
Yeah.
second part.
Yeah.
And from the second part, what it will go to the third,
Third.
u1 x2 plus this one, the h naught v, what is it, h naught v1 plus u1 x1, this will go to the third part.
Right. H not. No, no. So you'll the third part's inputs are here. No. So it will
No, no,
be
no. Now see, first line is the x1 x2 x3, okay.
right.
second line में v1 है.
So let's try to define them individually first
हाँ हाँ,
instead of
ये मुझे क्लियर कीजिए. हाँ.
yeah. So you have so tell me now what will be the value of this thing this yeah. So you have this H0 of 1. So tell me what will be the value of H1 of 1.
h1 of
H11.
h11,
Yeah.
it will be ma'am, yeah, u1 x1 plus h naught v1, it will go over there, plus plus this will go through a tan h function, and
Yeah.
then that value will be yeah, added to h2 v2, h naught v2.
Mm, H not V2. No, just I was thinking of just staying in this area first. Then we'll go to the next step.
Okay, okay.
So yeah.
So
So
what were the equations? Can I say the equations now?
yeah, so H so what I was asking for is suppose you have a hidden state here, anywhere
Uh,
here, some HI,
okay, okay,
some HI in the HI in the first layer. So there will be a superscript of 1. So what will be its value? Its value will be tan of H u1 into xi because you are at the ith time step plus h of I minus 1 with a superscript of 1
okay.
into this thing no v1
Now, can you please
that
write it?
okay yeah what I'm saying is this okay, just again remember that I'm writing it for the first layer.
Okay, okay, okay. Please write it.
Okay, this will be h minus 1. Yeah, something like this. So I don't know if you understood this or not. This means that I'm talking about in the first layer, any for any timestamp I, I'm
Okay,
calculating what is the value of the hidden state. What is going to be there in the hidden state. So that is going to
okay,
be h of I equal to tan of h. The multiplying matrix will be u1. You multiply it
okay.
with the current input xi. So u1 into xi. Forget the dimensions for now. Dimensions you can adjust, right?
Okay,
Hmm.
okay, okay.
Yeah, plus h of I minus 1, which is the previous hidden state, into V1,
Okay.
right? So this is going to be your first hidden state. Now from here, taking this as the input, you also have to calculate this hi for the second hidden state like this. Taking this as the input, whatever dimensions come from here, you take that as the input and do the exact same thing from this hi2.
Ma'am, all these things I have calculated. Can you please check? I'm sending you that thing also. Whatever you are
See,
saying, I have
we are way past time now. I actually have to leave, but yeah, that's why I was trying to explain to you how to go about it.
ma'am,
So,
ma'am, I've sent. Please check the mail. Yeah, you can see the figure. I have calculated it.
just tell me what the problem is very quickly.
Problem is that means I'm not understanding one two things. Please go to
Okay.
the figure. हाँ, देखो देखो मैम, नीचे जाओ. ये देखो मैंने किया है. A1
Hmm.
of t equal to U1 x1. A2 of t equal to A1 plus V1 H1 t minus 1. Is it clear?
Yeah. Okay. And okay, so this I if I remember correctly, this will be not U1 X1. This will be U1 X1 plus
Transpose.
V1 into H0 of t. I mean, okay, you have
Ma'am, I have taken this portion as A1. Please check this thing. In the figure. In the figure I have written A1, A2, A3 like that.
wait a minute. Oh my God.
Yeah.
Okay. A1. Okay. So Okay, I'm getting confused by the notations that you have used actually. So, uh, I mean, what is A1 here? What have you been
A1,
able
A1
to?
is suppose from this part from x1 x2 x3 we are going to the middle part. Okay,
Correct.
तो इन बिटवीन इंटरमीडिएट मैंने A1 ले लिए उसके बाद उसके बाद जब
Intermediate, there is nothing. No intermediate, only the weights are there. All you can do is define the h's. The
अच्छा
h values that are here. So this is h0. H0
ओके
means the initial starting state. You have
ओके ओके
h1, h2, h3
ओके
of the first layer. The superscript is for layer 1,
ओके
right? So you go back to the RNN definition and try to figure out what will be this h1, what will be this h2, what will be this h3.
नहीं मैम what is my question I'm telling you, can I say let the figure be here, okay, let the figure be there only,
Yeah, but
okay.
okay,
What I'm doing, E1 X1 is going over there, okay, U1 X2 is also going over there, U1 X3 is also going over there, is it
correct.
fine till now?
Yeah.
Now what is happening that U1 X1 when it is going to the intermediate state, सपोज यहाँ से ये मिडिल पोर्शन जो है मिडिल का सेकंड पार्ट में जब जा रहे हैं तो मिडिल का सेकंड पार्ट में क्या जाएगा एच नॉट वी वन प्लस यू वन एक्स वन विल गो ना इन द मिडिल पार्ट
Wait. I got confused. In the second part, middle part means what? These three, right?
हाँ दिस थ्री का मिडिल जो है मिडिल
Yeah. Middle one, this one.
हाँ मिडिल वन हाँ उसमें क्या
Yeah.
जाएगा इनपुट
What will go here is basically nothing but your H1, whatever
ओके
H1 you computed into V1 plus this X2 into U1.
एंड मैम यू वन इंटू एक्स वन दैट नॉट गो
No. That you have already computed inside this. So what you have to do is what I'm telling you is that just go back whatever sir taught. You don't need to explicitly go to my slides, but whatever slides sir has, just follow this one properly.
अच्छा
Okay,
मैम वो
everything
फिगर
is given here.
अच्छा अच्छा
So
अच्छा
at every time step, you only need the previous hidden state and the current input, nothing more. You do not need
अच्छा
to, as
टेक
you
द
are
प्रीवियस
saying, yeah. So where did the mail go? Yeah. So as you were saying in the second one, you do not need the input from here. It's all defined in the formula.
ओके ओके
All
ओके
you need is the current input here. X will be
एंड
the current one and hidden will be the previous one. That's it. All the
अच्छा मैंने
other
भी
things are automatically
ओके
computed.
okay I'm doing a wrong calculation that means
Yeah.
I'm
That's
thinking in
the
front.
only thing that you have to take care of. Go back to any book, any slides that you have that you are feeling comfortable with. Just pick
अच्छा
up the formula and just write it down. That's the only thing you have to do.
अच्छा अच्छा ओके ओके
Don't do more. That's what I'm trying to say.
अच्छा अभिषेक मैम मेरा
Hmm.
वीक 7 से भी एक क्वेश्चन है
Okay, I think we'll have to go now. I have something up now. It's already 15 minutes past. Uh, about what?
about one question about one question
On?
can I say the question
Okay, just I can just give you 2 minutes. Okay.
okay 2 minutes is more than enough
Okay. Tell me.
one sec I'm giving it one sec
Hmm.
week 7 yeah I got it मैंने I got marks but I don't know how I got marks मैंने एक अंदाजी से मैंने I did it
Okay.
हाँ let me go over there one sec हाँ a feature map 32 cross 32 cross 12 feature map okay
Okay.
is given as input to the pyramid pooling module okay
Okay.
which creates 4 different feature maps at 4 different scales.
Mm-hmm.
What is the number of 1 cross 1 convolution filters required for each scale?
Okay. See these calculations. Yeah, you have to work the math out. So what you can do is, so what you are saying is you are confused about how to calculate it. Is it?
How to calculate? I do not know the formula, and formula is not available in the slides also. I have gone through it.
Okay. Just send me the question. Let me go through it. Not now. Maybe in some time.
When? Okay. In
Yeah.
your mail ID. I'm sending in your mail
Yeah.
ID only.
Send it to me on my mail ID. I'll get back to you.
Okay, done, Mahesh, ma'am. Thank you, ma'am.
Okay.
Thank you.
Thank you. Okay,
Thank you.
so yeah, let's end the call today.
Okay,
We'll meet once again next week.
okay,
Thank you
okay,
all.
ma'am. Done, ma'am.
Yeah.
Thank you, ma'am.
Okay. Bye.